Now let's see how to correct the error. Detecting the error is simple. We have to say that there is an error and that's enough. But correcting the error is somewhat complicated compared to detecting the error. Let's see what we did for one bit error detection. So if there is a valid code, if there is one bit error in this code, then it is going to take us to an invalid code, and therefore between two valid codes we are just giving a gap of a distance of 2, so that if there is a one bit error, then it will end up here or to some other side, and if there is an one bit error, it will end up there, right? Therefore using a distance of 2 you are able to detect one bit errors. Now so the problem is this: let us say you have sent some code and we got a code which we got one of the codes which is present at this position. Now this particular invalid code is at a unit distance from this one as well as this one. Now the confusion is, which one did you send? So I'll just take an example. Let us say one valid code is 0000, right, and the other valid code is 0011, and when you are trying to send 0000, because of one bit error, the receiver has got the code 0001. Now by looking at this code, he definitely knows that it is invalid because it is not in one of the valid codes. But then where did we get this from? Did we get this from here or did we get this from here? Both are possible. He may not be able to guess, because a one bit error in this one will create this, as well as a one bit error from this one will create this. So we can only detect the error but will not be able to correct it. Correction means we should even be able to know what is the original data that is being sent. Here we'll just be able to know that the original data whatever is sent has been corrupted. We don't know which one it is. Therefore in order to detect this correct this one bit error, we might have to go and dig deeper. See this. So if you have to correct this, let us say there is a valid code, okay, and now if there is one bit error, let us say that one bit error is landing you up here, okay, and now we have to see in such a way that if there is some other valid code here, if that is also going to have one bit error, that one should not land up here. Then only we are getting the problem, isn't it? If we see that if there is a other valid code here, and if it gets one bit error, it should not land up here, it should land up in an other intermediate state, which means there should be a distance of 1 at least here. Now if you have any such arrangement, you will be able to correct one bit errors. How? See this: if you are sending this one and if you got one bit error, you will definitely land up here, isn't it? You will definitely end up with a code here. Now this code is closer to this one than to this one. This code is at one distance from here, but this code is at two distance from here. Therefore you can say that there is an error, and the error created, and therefore the original code is this. So you will even be able to correct it. You will be able to detect it as well as correct it. See, in error detection you will have only error detection, but in error correction you will be able to detect it as well as correct it. Now in this case, when the distance is 3, check this, when the distance is 3, when the distance between two valid codes is at least 3, it can be more than that. If it is at least 3, then we will be able to do single bit error correction, right? We will be able to do single bit error correction for sure. Now let's see how to do 2-bit error correction. 2-bit error correction. How to do this? How to perform this error correction? Now if you have to perform 2-bit error correction, whenever we are doing 2-bit error correction, it is not just 2-bit error correction. It can be 1-bit error as well as 2-bit error, which means it can correct maximum of 2-bit errors. Now assume that, see, in this one when I am explaining it, here my assumption was that only one bit will get corrupted. Based on that assumption, everything I did. How do I know that only one bit will get corrupted when you are sending the data? That is just an assumption, okay. Now when I am talking about 2-bit error correction, see this. So error, when you are sending a valid code, there can be maximum of 2-bit errors. Therefore we'll end up with a code which is at a distance of 2 in the worst case, right? See this. I'll just take the example and I'll explain it. Let us say this is a valid code and you are trying to transmit it, and because of 1 bit error it will land up somewhere here, right? It will give you a code which is one distance, it is at a unit distance from that one. Now this one has to be invalid, this one is valid, right? And now because of one more bit error, then again we might end up in some other combination. This also has to be invalid, right? And the problem is, if you have some other valid code, 2-bit errors should not land you up here, because if 2-bit error from this code is landing you up here and 2-bit error from this code is also landing up here, then you will not be able to say which one is the right one. You will not be able to correct, you will not be able to say from which code you got there. That is why having 2-bit errors should not take you there. So if you have any other next valid code, it should be having its own error codes, which means if 1-bit error happens to this, it should land you up here, which is an invalid, and from here if you have one more bit, which means from here if you have 2-bit errors, it should land you up here. Therefore, when you land up at different places from valid codes, then only you can know which valid code it is once you get the invalid code. That is how you can correct it. So now if you observe it, the distance between two valid codes in order to correct 2-bit errors is at least 5 here. See, 1, 2, 3, 4, 5. It is like some kind of energy levels in electronics. If you remember it, when these atoms are having electrons, they will be in fixed orbits and rotating, and as you give the energy, they will get excited from one energy level to other energy level, right? So it is like this. So from one energy level to the next energy level, from here to here, here to here, like that. Okay, and these are two nucleus, right? And now if you supply more energy, the electrons from here might go to that nucleus. Okay, that is about electronics, but it is very similar, so I took it. Okay, see this. Now what I mean to say is, if you are supposed to detect the errors, or if you are supposed to correct 2-bit errors, then whenever you get those 2-bit errors from this code, from this valid code, you might end up in worst case here. Therefore, this one is at a distance of 2 from here and a 3 from here. Therefore, you can guess that this is, since it is closer to this, the valid code must be here, right? Even if you get a 1-bit error, then you will end up here, right? And then this code will be at a distance of 1 from here and maybe 4 from here. Therefore, you will know that this is the answer. See, once you are able to design a error correcting code for 2-bit errors, it will even be able to correct 1-bit errors, because for 1-bit error distance of 3 is enough, but here you are maintaining a distance of 5. Therefore, it is already correcting 1-bit errors as well as it is able to correct 2-bit errors. Therefore, for 2-bit errors, the distance between any two valid codes, the Hamming distance should be at least, the Hamming distance is how much? 5, right? So for 1-bit error, the minimum distance has to be at least 3. For 2-bit errors, the minimum distance has to be at least 5. Now let's see what happens for 3-bit errors. 3-bit errors. So for 3-bit errors, if you are standing somewhere here, if it is a valid code, and with 1-bit error you might land up here, which has to be invalid, otherwise you will not be able to detect it. With 2-bit errors from here, you will land up somewhere here, which has to be invalid, otherwise you will not be able to detect it. With 3-bit error from here, you will be able to land up at some error code which has to be invalid, because otherwise you will not be able to detect it. Now I cannot directly have the next valid code here, because if you have a next valid code here, let's see what happens if I have a next valid code here. If you have a next valid code here, with 1-bit error you might land up here, isn't it? With 1-bit error from this, you might land up here, which will make us believe that the actual code might be this one, which got 1-bit error and got corrupted here, or the actual code might be this one, which got 3-bit errors and got corrupted here, right? Therefore, having it this close will lead to some ambiguity, because we don't know whether we got this error code because of 3-bit error from here or 1-bit error from here. So you have to place the next valid code at a sufficient distance so that we will be able to distinguish the cases, right? Therefore, we have to have it in such a way that if we have a valid code here, with 1-bit error it should be able to go here, with 2-bit error it should be able to go here, and with 3-bit error it should be able to go here. With 1-bit error, with 2-bit error and with 3-bit error it should be able to go here in such a way that these two should not touch. If what happens if these two touch, then a 3-bit error from this one will take it to error code, as well as the 3-bit from error from this one will take it to same error code. Therefore, when you get that error code, you will not be able to detect which one is the original actual right one, right? Now by having this sufficient distance, how much distance is it? 7. 1, 2, 3, 4, 5, 6, 7. By having this sufficient distance, you will be able to correct 1-bit errors, right? Because 1-bit error will be either here or here, and you will know which one it is. 2-bit errors, it will be either here or here, right? Or 3-bit errors, it will be either here or here. So depending on which one it is, you will know which one is the closest valid code and you can take it there. But then it cannot detect 4-bit errors, because if you are here and a 4-bit error occurs, you will end up here. Isn't it? You will end up here, and which might also represent a 2-bit error from here. Therefore, you cannot do that, right? Okay. Which might also go for a 3-bit error here, which you cannot do that. Therefore, if you are designing it for 3-bit error correction, then the minimum distance between two valid codes should be 7, right? Here the minimum distance between two valid codes should be 5. Here the minimum distance between two valid codes should be 3. Therefore, if you observe the pattern, it is very easy to derive that if we are going to go for t-bit error correction, then the minimum distance between two valid codes should be at least 2t plus 1, right? Greater than or equal to. If it is t-bit error detection, just error detection, not correction, then the minimum distance between two valid codes should be greater than or equal to t plus 1. So for error detection, it should be greater than or equal to t plus 1. For error correction, it should be greater than or equal to 2t plus 1. These are the conditions you are supposed to remember. Now, the problem is this. So as you have seen this, if you want to incorporate this error detection or error correction techniques in any code, we are supposed to increase the distance between the valid codes. Now what happens if you keep on increasing the distance between valid codes? The number of patterns that have to be left out as invalid codes are going to increase, which means given a code, you will be able to use only few of the patterns as the valid codes and most of them have to be left out as invalid codes. Then what happens? You might not be able to get all the necessary patterns that you want. For example, if I want to represent 10 numbers from 0 to 9 using 16 patterns using 4 bits, then how much distance can I give? I cannot even give a distance of 2, isn't it? So what I mean to say is this one. Let us talk about BCD, binary coded decimal code. In this code, how many bits are we using? 4 bits. Therefore, how many patterns we get? 16 patterns, which means all the patterns 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Now these 16 patterns have to be assigned to the BCD numbers from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Now the problem is, if it has to have this error detecting or error correcting capabilities, even if you want to have error detecting capabilities of, let us say, error detecting capabilities of 1-bit error detection, right? Now we just told you that if you have to have 1-bit error detection, the minimum distance between two codes should be greater than or equal to t plus 1. So what does it mean? The minimum distance between two codes should be at least 2, right? Which means if you take one pattern as a valid pattern, then you should leave out all the patterns which are at a unit distance from this, right? Now if you leave out all the patterns which are at a unit distance from this, you have to leave out 1, you have to leave out 2, you have to leave out 4, you have to leave out 8, right? Now 4 of the patterns are gone out of 16. Then how many are remaining? 12, isn't it? Now if you take this one as a valid pattern, see, I think you got how I got this. If you take 0, 0, 0, 0 as a valid pattern, right, then any pattern which is at a unit distance from it cannot be any other valid pattern. So what are the patterns which are at a unit distance from this? 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0. It is 1, 2, 4, 8. Therefore 1, 2, 4, 8 have to be eliminated. Similarly, if you take 3 as a valid pattern, which means 0, 0, 1, 1 as a valid pattern, all the patterns which are at unit distance from this have to be eliminated. What are all the patterns which are at unit distance from this? 1, 0 1 1, which is nothing but 11, I guess, right? So 11 has to be eliminated. Okay, and then what is next one? 0 1 1 1, 7 has to be eliminated. Okay, and what is next one? 0 0 0 1, 1 is already eliminated. What is next one? 0 0 1 0, 2 is already eliminated. Now check this, how many are totally eliminated now? 1 2 3 4 5 6, 6 are eliminated, only 10 are remaining, right? Now if you take 5 as a valid pattern, which means 0 0 1 0 1 as a valid pattern, then all the codes which are at a unit distance from this have to be eliminated. So one of the pattern is nothing but 1101, so 1101 is 13, so 13 is getting eliminated. Likewise, if you keep on eliminating, you will not be able to get 10 valid codes to represent these 10 bits, isn't it? So if I have so definitely it is not possible to get 10 valid codes. So what is the solution for this? So if you have to incorporate this error correction and detection capabilities into a code, you have to see that we have sufficiently large number of patterns available, so that even after assigning, taking out some of them as valid and leaving out some of them as invalid, our need should be fulfilled. What is our need? We have some information to represent, that is our need. So after taking out all this, the information has to be represented, right? So I'll just take an example. So how is this possible? How can we get the sufficient number of patterns? By increasing the number of bits in the code. Using 4 bits, you got only 16 combinations, and in these 16 combinations, if you have chosen 10 combinations as valid, you will not be able to give lot of gap between two codes, right? Two valid codes. That is why increase the number of bits. So one of the techniques which can be used to increase the distance between two valid codes is to increase the number of bits and to assign the extra bits the patterns in such a way that they will be meaningful. I'll just take an example and I'll show you. So one classic example is, we have already seen the gray code. In gray code, the distance between every two numbers is 1. I hope you remember. In gray code, the distance between every two numbers is 1. Isn't it? Unity. That is why it is called as unit distance code. Now what is the problem with that? If there is even a single bit error, that will take one valid code to the other valid code, so we will not be able to detect that error. Now how can I do manipulations on this gray code in such a way that the distance between two valid codes will be at least let's say 2. I want to increase the distance between two valid codes in the gray code. So this can be done by adding something called as parity bits. I'll take this example and explain you. See this? Now let me write gray code 0 1 and then 1 0. Here it is 0 0 1 1 and again 1 0 1 1 0 1 0 0. Here let me put 0 0 0 0 1 1 1 1. Let us say these are the 8 numbers, and we know that they represent from 0 to 7. These are the valid codes. Now the problem with this is the minimum distance between any two codes is 1. The minimum distance between any two codes is 1. That is also called as Hamming distance. Hamming distance of this code is 1. Hamming distance is nothing but minimum distance among any two patterns. You take any two patterns, any two randomly, and you see and you find out such for every pattern you take, for every combination of two codes you take them and you find out the minimum distance. That minimum distance is the Hamming distance. So here the Hamming distance is 1. Now I want to increase it. So one way to increase this one is increase the number of bits in the code in such a way that you add a bit called as parity bit. Generally parity is of two types. Some people will use even parity and some people will use odd parity. Even parity means we are going to add a bit in such a way that in such a way that the total number of ones in that pattern is going to be made even, then it is even parity. Or if the total number of ones in that in that pattern is going to be made 1, that is called odd, that is called odd parity. Let us go with even parity. So I am going to add a bit here in such a way that the number of ones in this entire pattern is going to be even. So if I add a 0, the number of ones is going to be even. Why? Because the number of ones is 0, isn't it? So what should I add here so that the number of ones in this pattern is even? 1, because then only the number of bits is going to be, number of ones is going to be 2. Now what should I add here? 1, isn't it? Are you getting this? 0, because the number of ones is even. So what should I add here? 1. What should I add here? 0. So I'm just trying to make it as even parity. So what should I add here? 1, 0, 1. Yes. Now after increasing the number of bits in some meaningful manner. What is the meaningful manner here? I am trying to make the number of bits as number of ones in this one as either even or odd. Now check the distance between any two chords. Now the distance between these two is 2. Earlier it was 1. Now the distance between these two is 2. You can check anywhere, the distance, minimum distance will be 2. Now what is the advantage of such a method? Now since the minimum distance or the Hamming distance of this code is 2, it can be used as single bit error detection. Got it? Single bit error detection can be done by using this code, because we are having a Hamming distance of 2. That was the requirement for single bit, right? Therefore we use several methods in order to increase the distance between the codes in such a way that we'll be able to use it for error correction as well as error detection. That depends on your requirement, right? But the most important requirement is, now in most of the, in at least in digital, which means when you are going for this storing numbers in or storing something in our computers, single bit errors are the most frequently occurring errors. Therefore the most important method is single bit error correction, 1 bit error correction, right? So if you have to correct 1 bit errors, I told you that the distance, minimum distance has to be 3. But then instead of using this method, which means getting the error code and then seeing how far it is from the other, we shall use some other method which is called as Hamming codes. So we shall see Hamming codes and how these things are evaluated. So what are the main important points that you should learn from this topic is, till now is, in order to detect t-bit error, the minimum distance between two valid codes has to be at least t plus 1. In order to correct t-bit errors, the minimum distance between two valid codes should be at least 2d plus 1. Okay, fine.
Hi, if you are planning to do masters, then doing masters abroad is better than doing masters in India. I'll give you all the reasons. So, first reason is, out of 1 lakh students who take GATE every year, there are only 500 seats in old IITs. So all the IITs put together have an acceptance rate of 0.5%, and IITs, universities better than IITs, they have very good acceptance rate like 30%, 40%, but all the IITs put together have an acceptance rate of 0.5%. And if you are working hard to get into IIT Bombay's ranking is 177 and IIT Roorkee's ranking is 400. If you are happy to get into IIT Roorkee, then getting into universities better than IIT Roorkee is easier compared to getting into IIT Roorkee. And looking at the salaries for computer science, for software jobs, if you have done your masters in computer science in US, the salaries are ranging from 80 lakhs per year to 1.2 crore per year. So even if you take an average of 1 crore per year, your savings will be much higher than the salaries in India. After taxes and your cost of living, you can easily save 40 to 50 lakhs per year. And in India, the maximum jobs that you get is around 30 lakhs. So your savings will be much greater than the salaries in India. And these are all the services that we provide. University shortlisting. So depending on your profile, we will shortlist what are the universities that you have to apply, and statement of purpose building, and then LOR guidance, and GRE and English test assistance, and education loan assistance. So you don't have to have any collateral, which means without any security, now you can get education loan. Getting education loan is very simple these days, and whatever the amount of fee that you have a range of universities. You can apply for 10 lakh universities, 20 lakh universities, or 50 lakh universities. But whatever it is, you are going to get complete education loan, and you can pay off your education loan in 1 year after you get a job. And then we do visa assistance, mock visa interviews, and then connecting with the university alumni. So now you might ask why we should join Game of Visas. So the answer is, we have 90% success rate, 99% success rate. And these are all the destinations that we guide the students to. So we guide students to any country that you want to go. So now it is not just USA. We guide to UK, Germany, Australia, Canada. So we guide students to all the countries. We work with all the destinations. And if you are interested in going abroad, you have to just drop us a message on this WhatsApp number 9494 555 454. Okay, thank you.